now we come to the first law of thermodynamics, and we can also expand on different thermal processes, right? So I'm going to cover the theory and then show examples of that, right? So the first law of thermodynamics says heat into a gas is equal to the work done by the gas plus the change in internal energy of the gas, right? Heat into the gas. So what does that mean? Let's say I have some fire under the container of gas right here, right? And then there's a flames here, right? So you are putting heat into the gas, right? So heat is coming in, Q into gas, right? So what's going to happen? Well, the molecules of that gas are going to be vibrating, agitating really fast, right? So in general, its temperature is going to increase. Why? Because temperature is a measure of the average kinetic energy of molecules, right? So as the molecules move faster and faster, their energy increases. So heat into a gas causes the energy of the gas to increase, delta E of the gas, right? But if the gas is touching the container, the container and also the piston, right? If the piston is not locked, it's not bolted to the walls of the container, and if the piston is free to move, then the gas will also want to push up on the piston and do work against the piston, right? So the volume of the gas is going to increase. It's going to push up on the piston, and by the volume increasing, that means the gas is doing work. So work by the gas is going to equal positive number, right? To give this some numbers, let's say Q into gas is equal to 100 joules. If the change in internal energy of gas is 60 joules, that means how much work does the gas do, right? So that's a simple example. So then work by gas is equal to 40 joules, right? Okay, so if there was another gas container, okay, let's say a similar container, but maybe made up of a different molecules or something, right? Let's say you put into that gas 100 joules of heat, and let's say the change in internal energy was 20 joules, right? How much work would that container do against the piston, right? So the work done by that container would be 80 joules. So this kind of brings us to the concept of efficiency of an engine, which we're going to touch upon more later in chapter 22 for engines, but we can kind of touch upon that quickly here. We can say which container is more efficient. Well, here you're putting in 100 joules of work. More of it is going into heating the gas, right? Less of it is going to actually the gas doing work. So what's the efficiency of this? 40 over 100. You're putting in 100. But the gas is doing 40 joules of work, so the efficiency is equal to 40%, right, for this container. For the other container, the efficiency is 80 over 100. 80 joules, for every 100 joules of heat you're putting into it, it's doing 80 joules of work. So this would be efficiency 80%, you see? So this kind of gives you an idea of what efficiency is. How much work is that system doing based on what you put into it, right? Okay, so how about if these numbers are negative? Let's say something like this, for example. Let's say instead of the gas doing work, let's say you are pushing down on the piston. So instead of there being a fire on the bottom, imagine now somebody is pushing down on the piston with a force. Okay, what's going to happen? So if you push down on the piston, right, the work done by the gas is negative. You're doing work on the gas. So I can say work on gas is 100 joules, and then the volume is decreasing, right? So the volume is decreasing, you're going downward. What's going to happen to the gas? Okay, so what's going to happen here? This equation, work by gas is negative 100, right? So work on gas is equal to negative work done by gas. Negative work done by gas. Okay? So then what's going to happen? Delta E of gas and then Q into gas. Well, what's going to end up happening by you pushing in, the temperature of the gas is also going to go up because you're making it, you're constraining the volume. The molecules are going to be bumping into each other. So it's still possible that the change in internal energy is 40, or maybe the change in internal energy is 20, right? So let's just say change in internal energy of the gas is 20 joules. Then how much work, what's the heat into the gas? So we can say heat into gas is equal to negative 100 plus 20, which is negative 80, right? That means what? Heat actually leaves the gas. So we can say Q into gas is equal to negative 80, but Q into gas is equal to negative Q out of gas, right? So that means Q out of gas is positive 80, okay? So then what ends up happening, Q into gas is negative 80, and then the 80 joules leave the system. Right? What you can do in these kinds of cases, so that you don't have to worry about too many negatives, is that you can kind of rewrite this equation, okay? You can say Q into gas is equal to negative Q out of gas, and W on gas. Negative W on gas. And then the change in internal energy, we always keep that as change in internal energy of gas. So then what we can do, take this to this side and take this to this side and write them as positive numbers. So the first law of thermodynamics can be expressed this way, or switch these two, we can say work on gas is equal to Q out of gas plus change in internal energy of gas. Okay? So you have two major forms of the first law of thermodynamics. For our first example, where we were putting in heat and the gas was the one doing work, this is more convenient to use because nothing is negative. You're putting heat into the gas is doing work, and then there's change in the internal energy of the gas. For this example, where I'm pushing in, I'm doing the work on the gas, and then heat is going to escape. Heat is going to escape. How much heat is going to escape? 80 joules. What if the change in the internal energy was 40 joules, right? This was 40 joules, and then this would be 60 joules. So if more of the work that you do goes into heating the gas, less heat escapes to the surrounding, right? That makes sense. If less of the work that you do goes into heating the gas, more heat escapes to the surrounding, and then the surrounding's temperature goes up, right? So depending on which one you want to be positive, then you can do it that way, right? What if you take the container of gas and you put it in a bucket of ice cold water, right? So imagine like this, and then there's a piston here, movable piston. So what's going to happen here? So this is ice water. Which one is easier to visualize now? So since the outside is cold, this time no one's pushing in and you're not putting in heat, but since the gas's temperature is hotter than the ice water's temperature, heat is going to escape out, right? Heat is going to escape out like this. So Q out of gas. Let's say Q out of gas is 60 joules. Okay? So Q out of gas is going to be 60, so perhaps this equation is better to use for this one. Work on gas. Q out of gas is going to be 60 plus delta E of gas. Okay, what's the most likely scenario on what's going to happen on the work on the gas? Is it going to be positive? Is it going to be negative? Well, it kind of depends on the delta E of the gas, right? We know the gas is going to cool down. So let's say the delta E of the gas is negative 20 joules. So this one is a little bit different here. Here you were actually doing work on the gas, and you were causing it to warm up, and depending on how much it warmed up, different amounts of heat would escape. Here, the heat is escaping because it's an ice-cold mixture, right? And then depending on what happens to its temperature, how much the temperature drops, right? Depending on the delta E, that's what determines the work on the gas. So if the delta E is negative 20, work on gas is 60 minus 20, that's 40. So then what happens there? Right? That means the work is done on the gas, the cylinder, the piston goes down, right? The piston goes down, the gas occupies less volume and it has cooled, and that makes sense. If it occupies less volume and the molecules are moving slower, then the weight of the piston is going to cause it to drop and it's going to go all the way down to zero, right? How about if delta E was negative 40? So then you're going to have work on the gas is going to equal 60 minus 40, and then that's going to equal 20. What happens? Then the work on the gas is less. That means the piston doesn't go down as much, right? So of course then the pressure of the gas is going to be changing. So it all depends on the circumstances of what's happening. Depends on what's happening to the pressure and the volume and the temperature, right? So then how about if the delta E of the gas is negative 60? Then the work on the gas is going to be what? 0. 0 joules. Well, what does that mean? This would take place if the piston was bolted. Piston bolted. That means the temperature of the gas would drop a lot. The change in internal energy of the gas would be negative 60, right? The temperature of the gas would drop a lot. In this case, the temperature of the gas is not dropping a lot. So if the gas's temperature doesn't drop a lot, the piston goes down more, right? And the pressure of the gas increases, right? Let's say the initial temperature of the gas was 300 Kelvin, and it goes to 250 Kelvin. Let's say the initial pressure in the gas was atmospheric pressure. Okay, what's going to happen to the final pressure? Okay, and then the volume is going to be, let's say the volume was, the initial volume was just V initial. Then we can call the final volume 1/3 of V initial. V final is 1/3 V initial. Okay, so we can say P1 V1 over T1 is equal to P2 V2 over T2, right? And then P1 is equal to 1 atmosphere. V1 is equal to V initial. T1 is equal to 300 Kelvin. P2 we don't know. V2 because the piston went down. Why did the piston go down? Because work on gas was 40 joules. Okay, so then the final volume is 1/3 of the initial volume, and then T2 was equal to 250 Kelvin. Okay, so then the V initial cancels, and then P2 is going to equal 250 over 300 times 3. So P2 is going to equal, this one cancels this 100, 250 over 100, 2.5 atmospheres. Okay, so in that case, you put the container of gas in an ice, it loses heat, its change in internal energy is negative 20, it cools down from 300 to 250, and then the pressure goes way up, and then the volume drops a lot. Okay, well, what if the change in internal energy was negative 40? And it goes all the way down like this. So V final is going to be 2/3 of V initial, right? So the piston doesn't drop as much. And then we can say, what happens to the temperature? Well, change in internal energy is negative 40. Here the change in internal energy was negative 20. So the temperature drops twice as much. So here 300 to 250, that's a drop of 50 Kelvin. So then you can go 300 to 200 Kelvin. So it's likely that if the initial temperature was 300 Kelvin, the final temperature is going to be 200 Kelvin, right? Here V initial cancels, P2 is going to equal what? The 2 cancels the 200 is 100, right? And then you're going to have here 100 goes over there, and then the 3 goes over there, over 300, right? In that case, the pressure stayed constant. So what happened was that since the volume didn't drop too much, the drop in temperature from 300 to 200 was such that it accounted for the decrease in volume, and then the pressure stayed the same. This is called the isobaric process. Isobaric. It's a process whereby the pressure stayed the same. The other one, the pressure dropped a lot. The other one, the pressure increased a lot more, from 1 atmosphere to 2.5 atmospheres, right? What would happen if the change in internal energy was negative 60? Let's see that. Negative 60. So work on gas is going to equal 0 joules. That means the volume is not going to change. What is that called? Isovolumetric. Isovolumetric. Why? Because this volume is not changing at all. So if the V initial, whatever V initial is, V final is the same. So what's going to happen there? Well, what's likely to happen to the temperature? If the delta E is negative 60, the change in temperature is 3 times greater than the initial one, right? So if the initial one was, T initial was 300 Kelvin, T final is going to be what? Well, the change in temperature here was 50 Kelvin, right? 50 Kelvin. If the delta E was negative 20, here the delta E was negative 60, 3 times the change in temperature. So that means if this is 50, this is going to be 150, right? So it's going to go from 300 to 150 Kelvin. V final is going to equal V initial. So what's the pressure going to be here? P1, so we don't even need P1 V1 over T1. We can just say P1 over T1 is equal to P2 over T2, right? So then if P1 is 1 atmosphere, T1 is 300 Kelvin, P2 is going to equal, we don't know, and then T2 is going to be 150. Okay, therefore the pressure is going to drop. So this is isovolumetric. P2 is equal to half an atmosphere. Okay, so when would this happen? This would happen if the piston was bolted on the 2 ends. You put it on a cold bucket of ice water. If the piston is bolted, the gas cannot do any work. No work will be done on the gas, and therefore the pressure will drop. Is it possible that the opposite happened? That the piston actually moves up? Well, you could possibly have that situation. So what would happen there? Then the Q out of gas is 60 joules, and change in internal energy is negative 80 joules. More change in internal energy than Q out of gas. Well, that means the gas is expanding, you see. So the work on gas would be what? 60 minus 80 will be negative 20. So if the work on gas is negative 20, that means the gas is doing work. So the work by gas is positive 20. Work by gas is positive 20, right? So then what's going to happen? What's going to happen to the pressure? So it's going up. Okay, so what's going to happen? T initial is 300. What's going to be the T final? Well, if the change in internal energy is negative 80, the change in internal energy is negative 20, 4 times the change in internal energy. So if this is a 50 difference, that's 200, right? A difference of 200. So the final temperature is going to be 100 Kelvin now, right? So T initial is 300, T final is going to be 100 Kelvin. How about the volume? V initial, whatever V initial, what's the final volume going to be? Remember, for a work on gas of 40, the volume dropped by 2/3. When the work on the gas was 20, it went from V initial to 2/3 V final, right? So this one is going to be, whatever V initial is, the final volume is going to be 4/3 V initial. So only 1/3 difference, right, of the volume. So this is actually 300, so 300 goes over there, so P2 is going to equal 300 over 300, and then the 4 is going to come down here, 1/4. So the 300 cancels, and then 1/4, so the pressure goes to 1/4 atmosphere. Oh, so this is P2 is 1/2 atmosphere, right? So if you put it in a cold bucket of ice water and the volume increases, the pressure will drop way big time from 1 atmosphere all the way to 1/4 atmosphere. The temperature will drop a lot from 300 Kelvin to 100 Kelvin, but the volume will increase, right? So any of these scenarios are possible depending on what happens, what the weight of the piston is, and what the characteristics of that gas molecule is, right? So you can see here from here, any kind of different general processes can happen. Some of them have specific names. They're called isovolumetric, isobaric, and then the other one is called isothermal. So in the next video, I will explain to you the differences of the isovolumic, the isobaric, and isothermal. Okay, thank you very much.